Today's topic will be this topic of linear discriminant analysis, also called as LDA for short. This is what you call as a dimensionality reduction technique. Now, a few weeks back, we covered a similar technique called as principal component analysis. So where we said, so this is also a dimensionality reduction technique. We do this to reduce overfitting and improve accuracy. And so in PCA, how it works is, out of a set of universal set of variables, you identify the most important variables. So that is what you call as the feature extraction. Okay, and so we said, yeah. So if there are n independent variables, we create n new independent variables, which are combinations of the existing variables and so on. Okay, so this is just a recap of the PCA concept. Now, linear discriminant analysis is also quite similar to PCA in that this is also a dimensionality reduction technique, but the difference is the way in which this technique works. Okay, so again, here also we reduce the number of variables while retaining as much information as possible. This is what you call as the supervised learning method. Supervised as in we already know the values of the target variables, and based on those values we take or reduce the available set of features to a smaller subset. Okay, but the thing is, this is used in a classification scenario. So PCA can be used in both prediction as well as classification, but this is used in a classification scenario, especially when you have classification involving multiple classes, right, or multiple class labels. That is where you can use the LDA. So for example, you have another technique called as logistic regression, where if you have a binary target variable, so something like a yes or no, 1 or 0, male or female, whether the person will default on the loan or not. So all these are binary classification situations. So there, you can straight away use the logistic regression. But what happens if you have multiple classes? So for example, let us say you're working on a customer segmentation or customer classification problem, and you have 5 classes, right? So in order to reduce your dimensions or reduce the number of variables and improve the predicting power of your multi-class classification model, you use the linear discriminant analysis technique. Okay, so how this works is, it will so in PCA, what did it tell? I told that it will create n independent variables out of the n existing independent variables, right? This works a little bit differently. How it works is, it will project the high dimension data to a lower dimensional subspace, which captures the essence of the data. It sort of transforms all those variables that you have, right? So for example, if your data set has 100 independent variables, then it sort of applies a transformation on those 100 independent variables and reduces those 100 independent variables into, let's say, some 20 or 30 independent variables, which capture the essence of all those variables. Okay, so that's how it works. And this projection, right, this can be used as the input to train the machine learning model. So rather than using all those 100 independent variables, what you'll be doing is, you will use those transformed smaller subset as the input to the machine learning model. Now I've got a Python implementation as well, which I'll be showing. So there you'll be able to understand this a little bit better. But this is the basics of the technique. Any questions here until now? Okay, I've got a bit more theory. So in order to use the linear discriminant analysis, we need to satisfy 3 assumptions. So first one is, we say that the variables should be normally distributed, and then all the variables should have the same variance, and there should not be any correlation between the independent variables. So that is to say that there should not be any multi-collinearity. Now, all of the assumptions that you see here are very similar to the assumptions you see in the linear regression model as well. So there also we say that the variables should be normally distributed, there should be no multi-collinearity and so on. Okay, so the reason for that is the technique itself is a linear technique. So that is why the name itself goes like linear discriminant analysis. Okay, so it sort of draws a line, in the sample space that you have in order to achieve that best classification. So that is why this technique is called as a linear discriminant analysis, and that is why the assumptions that you see for the linear discriminant analysis are very similar to the assumptions that you have for the linear regression technique. Okay. So just a small illustration of how this thing works. So for an example, just consider a data set containing two classes. Okay, so it could be something like 1 or 0, male or female, or yes or no, something like that. Okay. What the linear discriminant analysis does is it uses information from both the classes to create a new axis. Okay, so that is what I meant when I told that it draws a line. Okay, so basically what it is it creates a new axis. Okay, and it projects the data onto this new axis. Okay, and how does this happen? So the model seeks to find a linear combination of the input variables that achieves maximum separation between the classes and minimum separation within the class. Okay, so this is something similar to what we say in the clustering algorithm, right? So when we form clusters out of the data points, we say that the clusters should be formed in such a way that there is maximum separation between the different clusters and minimum separation within each cluster, so that each cluster is quite similar within itself, but it is very different from the other clusters. So that is how you achieve that very clean classification out of the data that we have. So just a pictorial representation of the technique. So let's say you have two classes x1 and x2. Okay, so you plot these on a scatter plot. So you have like the red colored circles are one class of the data, and the blue colored circles are the second class of data. Okay, so what the linear discriminant analysis does is it will draw a line across or spanning all these data points in such a way that the maximum class separation is achieved. So that is what you see here. So it will draw a line, and then it will project the different classes onto this line. Okay, but how does this process happen? So I mean, it's very simple to say that it draws a line and in such a way that it achieves maximum separation, but how exactly it happens is something a bit more mathematical in nature. Okay, so what it does is now I'll just give you an overview of this technique. Okay, but you don't have to bother too much about the internal mechanics of it because this is one way to do it. But as always, when we implement this technique via a statistical software package such as R or Python, it already has certain pre-built functions which just take in the input data set into independent variables and dependent variable, and so it does all these things internally. But it's just good to know how this thing works in the background. Okay, so that is what I have described here. So what it does is it first computes the within class and between class scatter matrices. Okay, and then once these matrices are calculated, it will calculate the eigenvector and the corresponding eigenvalues for the scatter matrices. So for the first step as well as the second step, there are certain equations and formula. And I have not put them over here because I don't want to complicate the contents of today's session, but feel free to refer to it at any point of time. I am sure some of you might be familiar with this concept of calculating the eigenvectors and eigenvalues. This is some plus 1 or plus 2 concept taught in school. And once we calculate these eigenvalues, we select the top k eigenvalues based on which components explain most of the variance. Okay, so what it does is it's something like just give you a quick illustration. So it's something like let's say you have eigenvalue 1 and eigenvalue 2, eigenvalue 3, eigenvalue 4, and so on. Okay, so each of these eigenvalues are what you call as the linear discriminant components, or the LDA components. Okay, and this value could be something like 0.5, this could be something like 0.4, then this could be something like let's say 0.05, and this could be something like 0.05. Okay, so the total of all this will sum up to 1. Okay, so like this it will calculate those different eigenvalues, and for each values if you just sum up those values, it will add up to 1. Okay, and out of all these eigenvalues, it will take those values which contribute which have the highest contribution. Okay, so this is a very crude example. This could also be something like, the EV3 and EV4 could be very small, infinitesimally small values. Okay, so in that case, what it will do is it will just take those values which have the highest contribution. Let's say, for example, it will just choose EV1 and EV2. Okay, and so let's say you had 4 variables totally in your data, right? So after you perform the linear discriminant analysis, it will just take these 2 components, which are like representation of all these 4 variables that you have. Okay, and when you do your predictive modeling, what you have to do is you need not use those 4 variables that you have directly, but rather you use these 2 components that you have. Okay, I'll show you how it works in Python, but this is how the internal mathematics works for the LDA technique. Okay, any questions until now on the concept? Yeah, so we select the top k eigenvalues. So the reason for doing that is those top eigenvalues carry the most information about the distribution of the data. Okay, and then again we create a new matrix containing the eigenvectors corresponding to these k eigenvalues, and then we perform a dot product, which is then given as the input to the predictive model. So this is how the mathematics works. All right, so I'll come to this a bit later. I'll just show you how this technique works in Python. Now as always, I will send you the presentation as well as the Python code at the end of the session, but just I'll walk you through the code and you can just see how we implement this technique in Python. Okay, I hope you guys are having a little bit comfort level or familiarity with Python. When I'm walking through these codes, is it like easy or is it too confusing? Should I change my approach? Any comments on that? I just wanted to know quickly.
It's comfortable, sir. We can understand.
All right. Okay. Thank you. Okay. So the approach that we follow is pretty similar to what we have been discussing over the past few sessions. First step is to load the required libraries. So the first library that we load, you see, it's a bit different. Okay. Until now, we have been loading the data set from the CSV file or the Excel file, which is stored on our local hard drive. But here we'll be loading a data set which is pre-built into one of the Python libraries. So you have this library called as sklearn. So this is short for scikit-learn. Okay, so this is a library containing your most commonly used machine learning algorithms. So anything like random forest or XGBoost or this linear discriminant analysis. So all these algorithms are present inside this library. But in addition to these algorithms, this library also has certain data sets. Okay, so if you have worked with R, you might be familiar with something called as this iris data set. Okay, and then there is this airline passenger data set and so on. So like that, Python also has certain pre-built data sets, and it is one of those data sets that we will be using in today's session. Okay, so I'm just loading this data set. So this data set is basically regarding different types of wines. Okay, so I'll show you once the frame has been loaded here. We just need to do some formatting steps before that. Okay, so next we import the pandas library to work with those data frames, and then at some point of time, if we need to work with arrays in our data, right, to actually load parameters onto the LDA function, we need to convert certain data points into arrays. For that, we'll be importing the NumPy library. Again, we'll be visualizing the results of the LDA. So for that, we'll be importing the matplotlib library. And so one thing with the linear discriminant analysis is that it cannot consider the categorical or the text-based inputs. Okay, so any categorical variables that you have in your raw data, you need to encode it in the 1-0 format. Okay, so this is also called as one-hot encoding. So they say convert the categorical variable into a continuous variable and so on. Okay, so for that, you can either use an if-else statement kind of thing, or the shorter way to do it is you import this library called as the label encoder. Okay, so it's just a simple function. You feed in your categorical data into this function, it will automatically convert it for you. Okay, so that is why we import this library to make this easier. And we also import the linear discriminant analysis function, which actually contains a method for the algorithm. And you just observe, I imported a separate group of libraries in addition to what we have over here. So here you can see that I imported this decision tree classifier. Okay, so why have I done that? I told you, once we do this linear discriminant analysis, the output is something like a reduced set of dimensions, right? And I told you, when we are actually building the model, we will not be using the raw data or the raw variables, raw independent variables, but rather we will be using the output of the LDA, right? So I will import this decision tree classifier, and as an input parameter for the decision tree classifier, I will be using the output of the LDA model. Okay, so just to repeat, the output or the result of the LDA will go as the input to the decision tree method. Okay, so that is why I'm importing the decision tree classifier. And as always, while doing any sort of a machine learning technique, we will just have to split the data set as training data set and test data set. For that, that also you can do it manually, or the easiest way to do it is import this function called as a train test split. Okay, so this will automatically split the data set into the training and testing data. So it will take random samples and do it for you. You don't have to bother about using a separate function for random sampling or anything like that. Okay, and then I'm also importing this confusion matrix function, because this, like I said, this is a classification problem, right? LDA is used for classification problems, and to measure the accuracy and precision of your classification models, you do it via the confusion matrix. Okay, I'll describe what the confusion matrix is a bit later, but again, this is an easier way of looking at the confusion matrix if you use the function directly. Okay, so let me just load the dataset into the workspace. Now I've just loaded it, and I've given it the name wine dataset. Okay, and the dataset is not in your conventional Excel or CSV format. So we just need to follow a couple of extra steps here. So first, what I'm doing is I'm extracting the independent variables from the data. Okay, so you can see that over here. Just open it for you. Yeah. So each data set, or each record that you see in this data set is a particular type of wine. Okay, and the numbers are basically what is the amount of each chemical component present in that particular wine. Okay, so that is what this data set is about. So you have the alcohol content, and then there is some kind of an acid, there is some ash, salinity, magnesium, I think this is phenol or something. Yeah, phenols, flavonoids. So like this, you have a lot of chemicals in each type of wine. Okay, and we have the values or the quantities of each of those chemicals in that particular type of wine. So these are the independent variables in the data. Okay, so using all this chemical quantity details, we'll need to predict what is the class of that particular wine. Okay, so I'll just show you how that works. So this is whatever you saw right now is the independent variables, right? So similarly, there's the dependent variable also. You have to take it separately from the data. Okay, so I'll just show you what are the classes of those dependent variables. So you have, if you just see on the right here, you have class 0, class 1, and class 2. Okay, so each of the wines that I showed you, right? So there are right here, yeah. So there are 178 types of wines, okay, or 178 brands of wines or whatever. Okay, and each wine falls into a particular category, either 0, 1, or 2. Okay, so what we need to do is we need to use those chemical quantity numbers to determine or classify what is the category of each type of wine. Okay, so we are taking the independent variables separately. We've taken the target variables separately. Okay, because that's just the way in which this rebuild dataset is structured. Okay, and then we just combine those independent and the dependent variable and put it in the data frame format. Okay, so once I do that, we'll just see what the final data set looks like. So I've stored this in a data frame called wine data frame. Okay, so you just see here, yeah. So until this variable called proline, right? So all these are the independent variables, and this class is the target variable or the dependent variable. So like I said, each is one particular type of wine, and it falls into one category like class 0, class 1, or class 2. So using all of these independent variables, we just need to classify under what category that wine falls. Okay. So these are certain preliminary steps that you have to follow. So once you have loaded the data frame, what you do is you define this function or you load this function in your workspace, which is the linear discriminant analysis function. Okay, so this function contains this method that I was talking about. So when I said this, yeah. So I said the LDA method follows these steps, right? So within class and between class scatter matrices, eigenvectors, eigenvalues, and so on, right? So all of these steps will be done in the background by this function called as the linear discriminant analysis. Okay. So I'm just loading this function onto my workspace, and I'm storing it in this variable called sk_LDA. Okay. And what I'm doing is I'm on this function, I'm just applying to the independent variables and the dependent variable. Okay. So independent variables and dependent variables, I'm just applying it, and the way I'm applying it is basically I'm using this sub method called as fit_transform. Okay. So the purpose of using this fit_transform is to transform those independent categorical variables into the numerical variables. So when you say class 0, 1, and 2, it can't understand directly. So that's why if you have any categorical type of data in your dataset, you just transform it into a numerical dataset. So that is why you have this particular line here, and you have applied this linear discriminant analysis method on this transform dataset. Now let's see what the results look like. So for that, you use this particular parameter, explained variance ratio. Okay. So now when I run this line, just observe what it has given. So it has given two numbers. Okay. So these two numbers are basically those two eigenvalues. Okay. So I told you, right, it will calculate those eigenvectors and eigenvalues. So this is what we call as the explained variance. Okay. So what does it mean? These two eigenvalues explain around 99% of the variation in your target variable. Okay. So the first value explains 68% of the variation. So this 0.68 is nothing but 68%. And the second value explains 31% of the variation in the dependent variable. So both of these two components alone of the LDA model explain a little over 99% of the variation in your data set. So all the remaining eigenvalues are insignificant. Okay, so this translates to something like, so this will be 0.68 and this will be 0.31. Okay, and the remaining 0.01 is split between all the other eigenvalues that we have. Because since all those things are insignificant, the model has just given us these two, this top two eigenvalues. Okay, and that looks something like this. Yeah. So these are those two eigenvalues, and this has been transformed into the dimensional subspace that I was talking about. Okay, so this doesn't make sense when you look at it directly. Okay, so this is something like a summarization of all the variables that you have. So you had 13 independent variables, right? So this independent variables data frame, if you see, contains 178 rows and 13 columns. So each of these 13 columns is one independent variable, and all of these 13 columns have been summarized into these two linear discriminant components. Okay, so these two are a summary of all those 13 independent variables. Okay, so just to visually represent the output of this LDA technique, I'll just plot a small graph over here. some pre-processing, and then plots. Yeah. So you see here there, I told you there are 3 classes in the data: class 0, 1, and 2. Okay. So you can see that this is how the LDA has achieved that classification. Okay. So the dark blue color here is one particular class, the green color is the second class, and the yellow color is the third class. Okay, so this is how so it has drawn all those lines and everything in the background, and this is the maximum separation that the LDA has achieved. Okay, but how does this actually translate when it comes to the predictive modeling scenario? I told you when you're building your predictive model, instead of using your raw independent variables, you will be using the summarized version of the independent variables, which is to say the output of the LDA, right? So how does that look like? I'll show you. So we'll be building a simple decision tree algorithm, and I'll be doing it twice. Okay, so first time what I'm doing is I am building the decision tree with the raw variables or without the result of the LDA. Okay, so let's see what that output looks like. I'm building the model and fitting the model onto the training data and applying it on the testing data. Now if you see, this is what those results look like. Okay, so are you guys familiar with this concept of confusion metrics? Have I mentioned this in any of the previous sessions? I know I have, but I'm not sure whether everybody was there in that session. How many of you are familiar with this concept of confusion metrics? Or should I explain it once again?
I'm good with it, Sai.
Okay, maybe I'll just give you a very short explanation. So we had like 3 classes, right? So class 0, 1 and 2, and similarly here also 0, 1 and 2. Okay, so whatever you have along this diagonal, right? So that is the correct prediction. So this is something like these 3 are your actual values, and these 3 are your predicted values. Okay, so when I say along the diagonal, what I mean is actually that wine belongs to class 0, and you also predicted, your decision tree also predicted that your wine belongs to class 0. Actually the wine belongs to class 1, and your model also predicted the wine belongs to class 1. Similarly for class 2. So whatever values you have along the diagonal is the correct classification. Anything that comes here, for example, let us say this is like, you get a number 10. Okay, so what that basically means is, actually in your data set you had 10 observations belonging to class 0. Okay, but those 10 observations your model predicted as class 1. So this is a wrong prediction that you have. Okay, so that is how this confusion metric works. So if you see the confusion metric that we have obtained, whatever comes along the diagonal, that is the correct classification. But you see this number 1 over here, and then you see this number 1 over here. These are the wrong classifications. So this number 1 basically means actually one observation belonged to class 0, but your model has predicted it as class 1. Okay, like what we had over here, this instead this 1. Okay, so this is also a misclassification. Now this is the case when we built that decision tree model on the raw data without using the output of the LDA. Okay, so directly I am using the independent variables here. See, now I will show you one more iteration of this decision tree, but in this case I will build the model on the output of the LDA. That is why I am using x_LDA. Okay, now let's see what this looks like. So I built the model. Now let's see what the results look like. So now you see you have variables only across the diagonal, 18, 17 and 10. Okay, so all the other values in the confusion matrix are 0, which is to say that your model has classified all the observations exactly correct. So your accuracy is like 100%. Now of course this is a very dummy data set kind of thing. This is not a real-time data. So that's why you get 100% accuracy. When you're actually working on a project, this might never be the case. Okay, but you can just see the effect before and after I used the LDA technique. So both the cases I'm using the decision tree algorithm only. Okay, but in the first case we have the decision tree model has made 2 mistakes. But in the second case, when I'm using the LDA as an input to the decision tree model, there are no wrong classifications. Everything has been classified 100% accurately. Okay, so this is where you use the LDA technique. So when you have a lot of variables, so 100 or 200 variables in the data, the model will get very confused when it is trying to find patterns out of those 100 variables. So that is why you project those 100 variables onto a smaller subspace, so that it is quite easier to make for the model to make sense of those patterns, and then thereby you improve the predictive power of the model. Okay. All right. So any questions on the method or the code, or any other questions? Okay, so that is what I had for today.